Hey class, Bob again, continuing discussion of forecasting. In our last video, we discussed the naive forecast. You see over here on the left-hand side, a naive forecast is simply using this week's sales, for example, to forecast next week's sales, or this month's sales to forecast next month's. It's called naive for a reason. It makes the assumption that the same situational factors, the same circumstances hold true from week to week, and of course that's not always the case. There may be a growth trend that naive forecast would not take into account. Um, well, there's a concept called responsiveness versus smoothing that we've kind of discussed, but I don't know that I've given it a name. The naive forecast, we say, is very responsive, meaning any real change that happens in our data, sales in this example, or demand in this example, any real change is captured immediately because we're using what actually happened entirely to produce our next forecast. And when we smooth things out, the most recent data only carries a fraction of the weight. So take this moving average 3, the 3-period moving average. If you think about it, this 45.1333 was calculated by going 1/3 times 44 plus 1/3 times 48 plus 1/3 times 44, which is how we, of course, take an average. So this very latest data, the 44 in week 3, carried 1/3 of the weight, where in the naive forecast it carried 100% of the weight. This 44 here carried 100% of the weight there. So the naive forecast is said to be responsive, meaning it responds immediately to actual changes in the environment. However, that also means it also responds immediately to noise in the environment or that random or inherent variability. So we want to smooth things out. So the more periods of time you incorporate into your moving average, the less responsive your forecast will be. So we could do a 10-period moving average, and think about that for a minute. We would take the last 10 pieces of data, the last 10 time periods of demand, and we would average them. And that would mean that the very latest data would only get 10% of the weight, 1/10. So it would not be terribly responsive. It would take a great deal of time for the forecast to reflect an actual change in the environment. Um, so would not be very responsive. It would, however, be smooth in that it would be canceling out that noise we talk about, those little bumps if you're visualizing a graph of, say, the stock market over time. So smooth versus responsive, these two things work against each other. One point we just mentioned that I want to point out is the most recent data in a moving average receives the same weight. It's just treated the exact same as the oldest data. So for example, if you look at this 45.333 again, these three numbers, 44, 48, and 44, each received equal weight. But one of the things you can do is give the most recent data a greater amount of weight. So we can do something called a weighted moving average. And what we could do, for example, is we could take, and I'm kind of arbitrarily deciding these numbers, but we could take 0.5 times the most recent data, which the most recent data would be B4. Okay, I need to put a times in there, times B4 at 44. So it gets half the weight, plus 0.3 times B3 gets a little less weight. A little older data gets a little less weight, plus 0.2 times B2. So the older data gets even less weight. See how this is different from the just basic 3-month moving average? What we're doing, and the concept I want to get across, is not that there's something special about these numbers I've chosen, but rather we're doing something that is intelligent. We are giving the most recent data the greatest amount of weight, or letting it affect our forecast more than the older data. So if I ask you, what do you think Microsoft will close at today on the stock market? Your first thing you want to look at is not last week's closing price, but what is the most recent closing price I can get my hands on? So it just should be intuitive that the most recent data is the most important data. So let's see, if we use that most recent data and give it more weight than the older data, then we can copy copy this formula down, and we can create a forecast as though we had been using that weighted moving average all along. Okay, and then we can measure the error of that forecast as well, just as we had been. Let's see, the error for the, let's call it WMA, the weighted moving average, is simply the actual minus the forecast, which the actual is B5 minus I5, the actual minus the forecast. Okay, and if we wanted to take the absolute value of that, I could slip a little ABS, put that in parentheses, and just combine those columns where I had been using two columns earlier. Now I'm going to take the absolute value of that difference, and it's 0.2. Now I can copy that formula all the way down, and this is the absolute error for each of my forecasts using that weighted average. Now I can do as I did here earlier. I took an average of those absolute values. I can actually copy that formula, because you know that as you copy from left to right and paste, the cell references go from left to right. In this example, they go from H to J. So if you look at the formula up here, it didn't copy I, it copied a J, because I moved over a couple of cells. So interestingly, this particular forecast, this weighted moving average, improved my forecast accuracy over those 52-week time period. Not by a lot, but it's a little better than the 3-month moving average, and a little better than the naive. Okay. The next thing I want to talk about is exponential smoothing, and I don't think I'm going to be able to get all that in on this video, so I'm going to cut this one off right here, and we'll produce another video in a minute.